So now we're going to start talking about dependent events. And two or more events are dependent if one outcome has an effect on the other outcome. So the example I have that maybe you haven't heard before is about Don't Eat Pete. I don't know if you've ever played this game, but this is a game that some kids will play. And so let me explain the rules so you can see what I mean about one event having an effect on the other. So what you do is you have a bunch of kids and they're all around this little game board, and one of the kids is it. And they will leave the room so that they can't see what everyone else is doing. And then all the other kids will pick one of the guys on the board to be Pete. So let's say that maybe they pick this middle guy and they're going to call him Pete. And the person that's it doesn't know that. And so there's an M&M. Oops, maybe we need like a yellow. There's an M&M on every single guy, including Pete. And so the person that's it will come back in the room and they'll start eating M&Ms. And they eat M&Ms until they end up picking the one that's Pete. They eat it and then everyone yells, "Don't eat Pete." And then they're not allowed to keep eating the M&Ms and then their turn is over. Okay, so my point about this involving dependent events is that when they start, they have only a 1 in 9 chance on this game board of picking Pete. But once they pick one, let's say they eat this purple guy over here and that one is gone. Well, now there's only 8 pieces left on the board, so now they have a 1 in 8 chance of picking Pete. And so that second M&M that they eat has a greater chance of it being Pete, and so it depended on them already having picked one of the M&Ms from the board. So that's a case where your first event is affecting your second event and what you pick. Okay, another common example that you might have seen before is picking 2 pairs of socks from a drawer without replacement this time. So as in you take a sock out and then, or a pair of socks out, I guess, and you don't put it back, and then you go and you pick a second pair. So the second pair that you choose, it's not going to be that first pair. You've already changed the situation. You've already taken one of the socks out of the drawer. So that second event is being affected by whatever you picked for the first pair of socks. Okay, so the way that you calculate the probability of 2 dependent events is you still multiply the 2 individual events probabilities together, but you just remember as you're doing it that the second probability was affected by the first. So it's the same formula, basically, if you're just thinking about multiplying the 2 probabilities together, but the way we read this formula here is the probability of A and B is equal to the probability of A times the probability of B, given that A has already occurred. Okay, so we've got our intersection here, and again, we know that A has occurred for that second probability. So here's my example for you. Let's say that you are picking cards from a deck, and as you take them, you're not replacing them. So what's the probability of picking a 10 and then picking a blackjack? So there are 2 events right there, and they're dependent because the cards are not being replaced. So we're going to find the probability of each event occurring. So first event is let A be the event of picking a 10. So let's think about how many 10s there are in a deck. And there's 4 suits in a deck of cards. So that would mean that there's 4 10s in a deck of cards, and there's 52 cards total. So the probability of picking a 10 is 4 over 52. The probability then of picking a blackjack, okay, given the fact that we've already selected a 10 out, is 2, because there are 2 blackjacks, right, because there's 2 suits that are black, and each of those suits has a jack in it, so there's 2. But now there's only 51 cards, so in this case, just our denominator has changed. Sometimes we need to be careful. Sometimes the numerator will have changed if the 2 events are also overlapping. Okay, so the probability of both events occurring is simply the product of those 2 probabilities. So we would multiply 4 over 52 times 2 over 51. And if we do that, we're going to obviously get 8. Oh wait, maybe I want to simplify ahead of time. I always like to do that. So 2 divided by 2 is 1. 52 divided by 2 is 26. Oops, that's supposed to be a 2. Ooh, okay. And then maybe I'll simplify again. 4 divided by 2 is 2, and 26 divided by 2 is 13. And that's probably as low as we can go. So 2 times 1 is 2, and 13 times 51 is, I believe, 663. And so that's going to be the probability of these two events happening, one right after the other. Okay, so here is an example that I have for you. It involves the game Don't Eat Pete. I think I have a picture here. So suppose that you're playing Don't Eat Pete with a friend. What is the probability of picking an M&M on a space that is not Pete on your first choice, and then picking Pete on your second choice? So remember, there's going to be M&Ms on all of them. I'll just go ahead and make it the same scenario. Let's say it doesn't really matter which one you pick to be Pete. So let's just say that the group picked this guy to be Pete, and you might just use that as you're working on this problem. So go ahead and think about this. What's the probability of picking M&M on a space that's not Pete on your first choice, and then on your second choice, picking Pete? Okay, so go ahead and pause the recording here and try this problem out. Okay, so I'm going to go ahead and put up our probabilities here of not picking Pete, and there's 9 M&Ms. That would be 8 different guys that they could pick that's not Pete out of 9 total guys on the board. But then the probability of picking Pete on the second pick, there's only one guy who is Pete, so that's going to be the numerator this time. And there are 8 to choose from because we already picked one. Say we picked that pink one right there. So we're going to multiply those two numbers together, 8 over 9 times 1 over 8, and we can, of course, divide out the 8s to be 1s, and then we've got 1 times 1 and 9 times 1. So the probability of both of these events occurring is 1/9. Okay, so that's it for dependent events.